So let's erase this for a moment, and let's talk about the problem with just taking delta t down, okay? Which is, at the end of the day, your computer has what's called numerical, it cuts off. It's IEEE double precision numbers. That's all it represents everything in. 16 place precision, okay? So you can only go down 16 decimal places. That's it. Okay? Now, there are some programs like Mathematica and Maple, which you can alter that precision and go down as many digits as you like. Right? You know, if you want 100 digits of precision, it'll do that for you. But almost everything that you typically work with, Fortran, C, whatever, all the other ones, MATLAB, they're all double precision. Okay? That's the default. 16 places. So how does that have an impact on what we want to talk about? Because you might say 16 places. I'm never going to get down there to worry about that. Maybe. But round off plays a role, and let's see how it plays this role. So let's go back to this idea here. dy dt equals if I were to approximate this differential equation, you know, I would normally say, this is what we started off with yesterday, which is what I'm really doing here. And by the way, this is exact, because now what we did yesterday was we threw this out and said, I'm not going to take the limit as delta t goes to 0. I would say dy dt is equal to this difference of position over time, slope formula. But before, we just threw this away to get our Euler formula. But now I'm going to say, well, let's keep in this error. I know what the error is generated from. Hey, the error is generated from that truncation we just erased. Okay. So we have this truncation error, but we have more than just a truncation error. The error is actually composed of two things, truncation and round off. In other words, when I go to represent that number right there, y of n plus 1, it's really not the exact number. It's some representation plus numerical round off. Oh, I do it like this. This is some number that's 10 to the minus 16. That's my round off. It only represents numbers to 16 decimal places. Okay? Okay. So when I go to think about evaluating that formula right there, what I really do is I evaluate it with some numerically generated numbers, which are not quite right. They're close, 10 to the minus 16, plus some error. And then we ask, what's in that error? Well, the error is composed of two things, round off plus truncation. Now, the truncation error we just talked about, but the round off now is the following. You know, you round off these numbers. That's my round off from computing that difference. Plus, here in the truncation, let me get this right, I have minus delta t over 2 sorry, let me try to write a second derivative if I can. Have this. Remember, I've divided everything by delta t here, so that's why I only have the one delta t. Okay. This is what I have. Two portions make up the error. So now what I'm trying to do is get a bound on this error. I'm going to try to see how big can this error actually get. So what I'll say is, you know, the biggest that this thing can get, it's less than or equal to some epsilon. This is numerical precision, it's the precision of the machine precision, 10 to the minus 16 or so. You can also bound then the absolute value of this to be, or minus e of n. That's the biggest it can be. And let's just say that the derivative is bounded by the following. M will be the biggest the derivative gets, which is the maximum value of this, of the absolute value of the second derivative. Somewhere in this interval of t to t plus delta t. So I say that these things take on some kind of as big a value as possible, some points, who cares what they are. And what I want to do with this is then say, well, how big or how can I bound my error? And this allows me to bound the error to say the error, the absolute value, is less than or equal to this E plus E over delta t plus what I have here is delta t over 2m. Okay? So this is the biggest the error can be. I put in, let's say, try to make it as big as possible. That's as big as it can be. Now notice E plus E is 2E. Okay? First thing I'm going to do with this thing, I'm just going to plot it real quick. And this term comes from what? Numerical round off. This term comes from what? Truncation. So the truncation grows like t, delta t. Say it goes, there's a line, some slope. And this goes like 1 over delta t. Tell me what happens when delta t goes to 0. Yeah, the thing blows up. That thing looks like this. So you have your curve that sort of does this. There's your error curve. So you start thinking, if I want to just get more and more accurate solutions, I just take delta t to be smaller and smaller and smaller. And at some point, you hit numerical round-off. Numerical round-off says as soon as you hit that point, your error is actually increasing. Not because of the truncation, but because now I have this round-off that I'm doing. And I'm actually not only going to grow, but I'm going to go very fast towards infinity. It's a problem. Where is the best point? There. Now, I'm trying to find the minimum of that curve, right? So the minimum of that curve, what you could do is just take that formula there and say, I want to take this, differentiate with respect to t, set it to 0, and I know it's the minimum because there is no maximum error. You can make as big error as you want. No upper bound. Okay? It is a lot like life. Okay? No upper bound, but there is a minimum error you can make. There it is. You do that, and then you get a formula out that there, what you say is delta t is equal to 4, just round off over m to the 1/2. Okay? There you go. So if this is 10 to the minus 16, then you take square root of that, it's 10 to the minus 8. So the smallest error you can make, you do not want to take time steps smaller for this simple scheme, smaller than 10 to the minus 8. If you take a small step smaller than 10 to the minus 8, your actual error is going up now. Okay? That's it. So you see, numerical roundoff can play a role. Typically, we're not going to ever try to get down here. We're going to say, I'm okay up here. I want big delta t's. Why do you want big delta t's? Because if you take big delta t's, you march forward your solution much faster into the future. And you get your answers quicker. You can go out on Friday night instead of sitting in front of your computer.